We're going to start the lecture on Chapter 10, Energy. Today we're going to focus on 10.1, the nature of energy, and 10.2, the relationship between temperature and heat. So let's take a look at the nature of energy to begin with. We know that energy is classified as either potential energy or it's classified as kinetic energy. Potential energy is due to position or composition. Kinetic energy is due to motion and depends on two things, mass and velocity of the object. So this equation that you see here for kinetic energy, 1/2 mv squared, which is mass times velocity squared, is one that gets used quite a bit in thermodynamics and in physics class. So you may have come across this before, probably in your freshman introduction to physics course. We need to remember that the potential energy of a system plus the kinetic energy of a system is always going to equal the total energy of the system. That leads us to the law of conservation of energy, which states, just like most of the laws of conservation, depending on what we're talking about, this time it's energy, energy can neither be created or destroyed, it can only be changed in form. And we're going to find that all the energy in the universe is considered a constant. Okay, this table came from www.diffin.com, and this just compares and contrasts kinetic and potential energy, and I thought it would be a good source for you to go back to. The definition, of course, that we just covered is kinetic energy is the energy of a body or a system with respect to motion or the particles of the system, where potential energy is stored energy or system due to position. Relative to the environment, kinetic energy of an object is relative to other moving and stationary objects in its immediate environment, where potential energy is not relative to the environment of an object. You can transfer kinetic energy because it can be transferred from one moving object to another in collisions. Potential energy is stored, so there's no transferring of the potential energy. Examples of kinetic energy would be flowing water, such as when the falling from a waterfall, where the potential energy is at the top of the waterfall right before the water goes over the edge and falls to the bottom. We measure both of them in the same units, which the SI unit for energy is the joule. The determining factors, as we said before, in kinetic energy is going to be the speed or the velocity and the mass. Potential energy is the way it's stored, so it depends on the height or the distance in the mass. So let's take a look at initial position. The initial position in this picture, ball A is higher than ball B. So ball A has higher potential energy than ball B because it's a higher position. The final position. So A has rolled down the hill. The potential energy that was in A has now been transferred to B. So that potential energy has been transferred. And when we look at it, we have to ask, well, if it was transferred, then where did it go? Did all of it go to B? Well, not all of it went to B because we have friction due to this surface right here. It looks like a grass. So not all of the energy that A transferred went into B to increase the potential energy of B. Some of it was given off as frictional heating, and that's going to be important in the next part. Okay, work. Work is defined as force acting over a distance. So work has been done on B. Why? Because the potential energy of B has been increased, so work has been performed on B. Let's look at the law of conservation of energy. Law of conservation of energy, remember, states that nothing energy-wise can be created or destroyed, so this total energy in the system must remain the same regardless of the pathway. What do we mean by the pathway? Well, a while ago we said, what if this were green? So this is grass. So the amount of friction on that hill, you can imagine trying to roll down that hill and it being grass. What if it was muddy? Would the amount of friction be different? Of course it would. What if it was ice covered? We know that the friction would be reduced drastically. So it doesn't matter where the energy is transferred to, whether it's transferred to a lot of friction or little friction, or to the ball B, wherever it is transferred, the total energy is the same regardless of what this pathway is. The total energy that A was able to give to B and to the pathway remains the same. Okay, so let's take a look at state functions. A state function is a property of a system that does not depend on the pathway. So energy is a state function. It's the same amount of energy in the system no matter where the energy gets transferred, whether it's a slick slope down here and it's ice and most of the energy is transferred to the ball B, or if this is mud and most of it is absorbed into the pathway itself and very little is transferred to B. The total amount of energy is always the same, so that's a state function. Okay, so let's take a look at work. Work is not considered a state function, and heat is not considered a state function, because the distribution of the heat, whether it's in friction or work done on B, depends on the surface of the pathway. So let's talk about the relationship between state functions, being a state function and not being a state function when it comes to the example given to you in your book. So when we look at the distance between St. Louis and Denver, Colorado, there's lots of different pathways we could take. And even if we did stay on this one pathway, we can go ahead and move the pathway. Let's say we move the pathway, and this is how we go instead, is through this pathway. So it doesn't matter. The pathway can change. But if we look at the pathway that we're going to take, let's say we take this in the summertime, and we travel this pathway, and it is a nice dry road the whole way, all the way to Denver, Colorado. Or let's say that we take this pathway and it's ice covered. So we have this pathway that we can take, but the conditions of the pathway could depend drastically on the weather and the time of year that we take the trip. Let's take another look at the relationship between St. Louis and Denver. This is a look of the relationship between St. Louis and Denver on Google Earth Pro, and this is really cool to mess with. So you can see the globe, and we're going to see if I can turn it this way so we can see. I've drawn the pathway between St. Louis and Denver, so let's look a little bit closer. And what I wish this would show you, and it doesn't, but what I wish it could show you is actually the elevation. Because it doesn't matter what happens when I go from Denver to St. Louis or St. Louis to Denver, what pathway I take, one thing is going to stay exactly the same. And let's take a look and see if we can move this about, tilt this just a little bit more. You can tell I'm really, really good at video games, right? Because I can control this. Yeah, right. Okay, let's go. And as we tilt this and turn it, we look at the topographical layout of the United States. And you notice that over here we have some hills, some of the darker areas here, some hills in Missouri. So we get over here, and you notice that this ridge right here, of course, are the mountains, the Rocky Mountain, part of the Rocky Mountain line here. And you know that Denver is popular for skiing and snowboarding, and the reason for that is because it is so high in elevation compared to what St. Louis is. And like I said, I really wish this would work to where I could look at it this way and show you the difference in elevation. But from St. Louis to Denver, Denver's much higher in elevation than what St. Louis is. So while the pathway between St. Louis and Denver is not a state function, the elevation, the total difference between the elevation between St. Louis and Denver is a state function, because it doesn't matter how we got there or what pathway the pathway was like, the overall elevation is different. So that's just the example that your book uses. It may help you to understand state function a little bit better. Okay, so let's go back to the PowerPoint and look at state functions a little bit more. So is this a state function, the distance traveled from one location to another? And with using the example that we just looked at, we have to say it's not, because it depends on the route that you take. Well, what about a change in elevation? And the answer is yes, it is a state function, because it's always the same and it doesn't depend on the route you take. No matter what, the difference in elevation between St. Louis and Denver will not be different, whether it's snowing or whether it is raining or sunny. And no matter what the pathway is to get there, that state function of elevation is always going to be the same. All right, section 10.2 talks about temperature, and heat. So temperature is a measure of the random motion of the components of a substance. So when you take the temperature of your body when you see if you're sick or not, what you're actually measuring in degrees is the measure of the random motion of the components. So the faster the components move, the more energy that there is bouncing around in there, the higher the temperature is. So in this example, the temperature of 90 degrees Celsius and 10 degrees Celsius, there's going to be a heat transfer, and it's always going to be from warmer to colder. So with this heat transfer from 90 degree water to the 10 degree water due to the motion, how are we going to measure that heat transfer? Well, we're going to measure that heat transfer by taking the temperature. So let's look at heat. Heat is a flow of energy between two objects due to a temperature difference. And it's the way in which thermal energy gets transferred. And we always go from a hot object to a colder object. So if we look at this reaction vessel here that we looked at before, so we have hot water on one side and cold water on the other, and if heat can be transferred through this plate that's here in the middle, what is going to be the final temperature of this system? So we have two different settings. We have an initial hot water temperature of 90 degrees Celsius, and we have an initial cold water temperature of 10 degrees Celsius. So after we let that set for a little bit, what's it going to be on each side? Because it's going to go until they have an equal temperature. So we're just going to do the average of this to find that out. So 100 degrees is what it would be added together, divided by 2. So this process is going to go on until we reach 50 degrees Celsius in each container. In your book, the formula they give you says the temperature final is equal to the temperature initial of the hot plus the temperature initial of the cold divided by 2. And if we take a look at the next picture, we see that that transfer has occurred and has completed because the water on the left side is equal to the water on the right side.